Let's take a look at the shapes of cycloalkanes. Okay, so let's start with the simplest cycloalkane, the one with 3 carbon atoms. So we have these 3 carbons in a ring, cyclopentane. Here's the Lewis structure, and here is the line angle drawing. Since we only have 3 carbons, the molecule will be planar. But there is a problem. As you know, in this triangle, so from the geometry in this triangle, you know the angle, the inner angle will be only 60 degrees. But for carbon atom that has 4 single bonds, the tetrahedron shape carbon, the bond angle should be 109.5, right? So we have tetrahedron carbon at each corner. Theoretically, we want 109.5 bond angle. But we have to force these 3 carbons to form this 3-membered ring. So we need to somehow squeeze the carbon-carbon bond in order to make the 3-membered ring. As a result, cyclopropane has a relatively big angle string. Okay, the bonds, the carbon-carbon bonds, are not really straight. They are bent to some extent due to the angle string. So cyclopropane is not as stable. Next one, the ring with 4 carbon atoms, is called cyclobutane. And here's the Lewis structure. The line angle drawing is a square. And as you know, the inner angle for a square is 90 degrees. It's still smaller than 109.5. So the shape for cyclopentane is not planar anymore. The 4th carbon will be pushed out of the plane, and cyclobutane is in this puckered shape. Okay. Again, we still have some angle string, and the cyclobutane is not as stable, but of course it will be more stable than cyclopropane, but still not as stable. The next one, the one with 5 carbon atoms, is cyclopentane. Lewis structure is like that, and the line angle drawing has a 5-membered ring. Similar to the previous examples, the inner angle for a 5-membered ring is 108. It's slightly smaller than 109.5. So the shape for a cyclopentane is not linear. We have 4 carbons in one plane. The 5th carbon will be pushed out of the plane to release any angle string, and it's in this envelope shape. Okay. Moving on to the next one, cyclohexane. Okay, the one with 6 carbon atoms. Lewis structure and the line angle drawing, 6-membered ring, a hexagon. This molecule will have different shapes. Okay, so the first 2 are called chairs. In chairs, we have the 4 carbons in the middle are in one plane, and one carbon to the left will be going either up or down, and the other carbon on the other end will be going to the opposite direction, down or up. So they look like a chair. So the four carbons will be the seat, and one carbon going up will be the back, one carbon going down will be the leg. Okay. The other shape for cyclohexane is called a boat shape. In the boat shape, four carbons are in the plane, and the two carbons on the left and on the right will be pointing to the same direction. Well, the boat shape is not as stable as a chair because the hydrogen atoms on two carbons on two ends, carbon 1 and 4, they will be very close to each other and there will be some repulsion there. So boat is not as stable. Chairs are the preferred shape for cyclohexane. So now you will need to learn how to draw these two chairs. Okay, so let me show you how to do this. In the chairs, we have 6 sides. 2 sides will be parallel to each other. So these two, the first and the fourth bonds, will be parallel to each other. Next, the second and the fifth bonds will be parallel to each other. The third and the sixth bonds will be parallel to each other. So you are basically drawing parallel lines to each other to make this 6-membered ring in the chair shape. Similarly, for the other chair, okay, the first and the fourth bonds parallel to each other, second and the fifth parallel, third and the sixth parallel to each other. Okay. Now something interesting about the chair shape for cyclohexane ring. Remember, on each carbon there are 2 hydrogens. So on each carbon in this chair, we must show 2 bonds. Okay? So I just draw 3 lines vertically going up. And these bonds, these 3 bonds that are going up, they are on the 3 up carbons. And they are alternating, meaning they are on carbon 1, 3, 5. They are not adjacent to each other. Okay? And the other 3 that I just added, the yellow bonds, they are vertically going down, right? So they are also alternating on carbon 2, 4, and 6. Okay, so basically we have these 6 bonds that are going directly up and down vertically, but they are alternating 1 up, 2 down, 3 up, 4 down, 5 up, 6 down. Okay? These bonds that are vertically going up and down, we call them axial positions. Okay? Axial positions. So on each of the carbon atom, we have drawn 1 bond. Where is the other bond? The other bond will be sort of on the equator of this ring. So let's see them. And these are called equatorial positions. Okay, equatorial positions. Please make a note here. On each carbon atom in cyclohexane ring, we must have one axial position, one equatorial position. Okay? So if you draw axial already going up and down vertically, the other bond on the same carbon must be equatorial. Equatorial is sort of pointing to the equator of the ring. The second note you need to make here is that on each carbon, there must be one bond going up and one bond going down. So, if the axial position is up, the equatorial position will be sort of going down. It's equatorial, but it will be tilted down a little bit. And if the axial position is going down, the equatorial will be up. Okay, it's still equatorial, sort of tilted up a little bit. Okay. Now, a couple more words about equatorial position. So if you take a look at the right-hand side, the two equatorial positions, equatorial bonds that are shown here, these bonds are actually parallel to the two black bonds in the ring, the two black carbon-carbon bonds in the ring. So now in the right-hand side drawings, the four black lines are parallel. So let me show you the other equatorial positions. So these blue lines are parallel to each other, four blue lines. Two are from the ring, carbon-carbon bonds. Two are the equatorial position on two carbon atoms. And then the last two equatorial bonds in red, they are parallel to the red bonds, carbon-carbon bonds in the ring. Okay? So equatorial positions will be parallel to one of the carbon-carbon bonds in the ring. And if we have hydrogens or other substituents on the equatorial position, it will be more stable. Okay, so equatorial positions means the more stable position. Okay, I will explain why in just a minute. Alright, next, let's take a look at the chair flip. Chair flip means we are going from one chair form to the other chair form. Okay, so if we start with this, we do a chair flip, we will get the other chair, which means we are flipping the down carbon up and we are flipping the up carbon down. Okay, I will show you how to do this in class using the molecular model. But one thing you need to keep in mind is look at the red bond. In the first chair form, the red bond is pointing down in the equatorial position. After the chair flip, the red bond is still pointing down, but it's an equatorial position. Okay? So in the chair flip, axial becomes equatorial and equatorial becomes axial. Okay, so the blue bond, it was equatorial, going up. After the flip, it is axial, but still going up. Okay? So if I number all the 6 carbon atoms, you see where they are now. Look at the carbon 1. It was a down carbon before flipping. Now it's an up carbon after flipping. For carbon 4, you see the equatorial red bond becomes axial red bond, but the red bond is going down. That doesn't change. The axial blue bond on carbon 4 becomes equatorial blue bond on carbon 4, but the blue bond is going up. That doesn't change. Okay? So, as I said, in the chair flip, axial becomes equatorial and equatorial becomes axial. That changed. But what didn't change? An up position is still up. A down position is still down. Okay, that doesn't change. So keep that in mind. Now let's take a look at this methyl cyclohexane. Okay, it's a substituted cyclohexane. More specifically, monosubstituted cyclohexane. It has only one substituent. When we draw the chair for this compound, let's say if we have this chair, I put the methyl group on axial position. When we do the chair flip, now the methyl group will be on equatorial position. But I start with methyl going up. I ended up with methyl still up. Okay? Axial becomes equatorial. Up is still up. Now, just now I mentioned that equatorial is more stable. When we have a bigger group, this is the truth. Again, experimental data show that at room temperature, 95% of the molecule exists in the methyl equatorial. Okay, so 95% of the molecule have the equatorial methyl. Only 5% of the molecules have axial methyl group. So why is axial not stable? So look at the hydrogen that's also on equatorial position, 2 carbons away from it. Okay, so suppose this methyl is on carbon 1. So the hydrogen that's shown here will be on carbon 3. These 2 groups, the methyl group and the hydrogen, both are pointing up. Okay, so if they are relatively big, imagine their electron density will have some interaction in the area in between, and there will be repulsion effect for those electron density. So we call this as 1,3 diaxial repulsion, which will make the axial position relatively unstable. And because of this repulsion, the bigger group doesn't want to be on the axial position. That's why this methyl is much bigger than the hydrogen. It prefers the equatorial position. If we have an even bigger substituents, like in this molecule, a third butyl group, a tertiary butyl group that's attached to the cyclohexane ring. The tert butyl, the bigger or the bulky group, tend to stay on the equatorial position. And it was found that 99.99% of the molecule in tert butyl cyclohexane stays on the equatorial position. So equatorial means more stable.